fellow assassins, to another episode of the Dark Assassins podcast, the show that dives deep into not just technology, but the concepts, software, and procedures behind it all, and explains it so simply that even your grandma can understand it. As always, I'm your host, the Dark Assassin. Now, before we get too far into this episode, I do want to wish all the mothers out there a very happy Mother's Day. In case you didn't know, I guess newsflash, it is Mother's Day on Sunday. This episode, of course, comes out on Saturday. So if you did forget, I guess you still have, a few hours to make something happen. But yeah, so happy Mother's Day to all the mothers out there. Now for this episode, I wanted to kind of touch on optimization. Now, if you've ever gone down the optimization rabbit hole like I have on many occasions, you will certainly run into the conundrum of, do I optimize for memory usage or do I optimize for performance? Because in a lot of cases, you'll run into a situation where you could use less memory, but it'll probably cost you in terms of performance because you'll have to do some additional computations and whatnot. Or you could optimize for performance, but because you're already essentially kind of pre-computing some of those things that you would otherwise have to compute during the processing, you take up more memory. So there's always this kind of like trade-off. Well, not always, but generally there's some sort of trade-off when it comes to optimization. Now, if you've seen the footprint of modern software, I think you're probably well aware of what most modern software development companies opt for when it comes to performance versus memory usage. Although in fairness, some apps are just garbage and they use a lot of memory, so I don't really know what they're optimizing for. Probably weren't optimizing for anything, looking at you Electron apps. But the thing of it is, if you do want to go down this optimization rabbit hole, which I do highly encourage you do because it is very fun and very rewarding, you'll like I said, you'll run into some of these issues. So in this episode, I kind of wanted to break down some of the trade-offs, some of the techniques that you can use for optimizing for both performance and memory usage, and then kind of compare and contrast them, and also maybe how you can find a good balance. Because like the meme goes, whenever you're in any kind of corporate business meeting, you can sound like an absolute genius most of the time if you can somehow find a way to work in. I think if we just can find a balance here, as long as you can kind of like throw that in there, people will be like, yeah, this guy knows what he's talking about. But anyway, with that out of the way, let's get into our trivia question for the week. So I wanted to give a softball. This is going to be a very huge softball for all the C developers out there. So if you're a C developer, if you don't get this one right, well, I don't really know what to say. So this week's trivia question is a simple true or false. So true or false, using malloc guarantees the memory you receive will be initialized with all zeros. So is that a true or is that a false statement? And that is your trivia question for the week. Now, we have a few different cybersecurity related news stories that I did want to touch on in this week's episode, one of which being the cybersecurity tip because it kind of fits, I think, pretty nicely. But the first one is this news story that came out this week about wormable AirPlay, which essentially enables a zero-click remote code execution exploit on Apple devices on public Wi-Fi. Now, before you run screaming to the hills being terrified, rest assured that this vulnerability has already been patched and software updates have already been pushed, and actually kind of a while ago. And the reason for this is thanks to responsible disclosure. Now, if you're not aware of what that is, if you're not really into the cybersecurity world, essentially what that means is if you're a security researcher, or you're hunting like bug bounties or things like that, the idea of responsible disclosure is essentially that whenever you find some sort of vulnerability like this, you go to the company that, or the developer, or whoever is responsible for the software, and you basically disclose all the information that you found, what the vulnerability is, how to exploit it, all that good stuff. And then you kind of give them like a set amount of time for them to patch the vulnerability, which in some cases companies they just don't. In which case then you can just release it to the public. But most of the time, at least most companies should, when they get a reasonable disclosure, responsible disclosure like this, that they do take the time to patch the vulnerability, push updates, and then once those updates are pushed, then the security researchers that discover the vulnerability can then kind of like publish their findings to everyone. And this is in contrast to the nefarious or black hat type of, I guess at this point they're just kind of like hackers, where they don't disclose the information to the company and instead, create some sort of exploit and then, sell it on the dark web or whatever for lots of money. Now, this is one of the reasons why bug bounties kind of became a thing, was to counteract the whole, black market vulnerability kind of marketplace. Because if it kind of makes sense, right? Like if you want to hunt vulnerabilities and get paid for it, I would like to think your initial intention is to be for the good of humanity. But at the end of the day, if you're just trying to get a payday, I mean, if the only people paying you are the bad guys, then I mean, that's where you're gonna go to get paid. So that's one of the reasons why bug bounties kind of became a thing, but also to try to incentivize people to find bugs and vulnerabilities in software. Because if there's an incentive for like your average user, to get paid if they find a bug or some sort of vulnerability in a piece of software they're using, they might be a little more likely to kind of poke and prod and do things that maybe you're not supposed to do with that software to try to break it in order to maybe get some money out of it. So those are just kind of some of the reasons why bug bounties exist. But anyway, back to responsible disclosure. So this vulnerability was responsibly disclosed, and like I mentioned, patches for this vulnerability have already been pushed out for all Apple devices. So this includes iOS 18.4, iPadOS 18.4, iPadOS 17.7.6, macOS Sequoia 15.4, macOS Sonoma 14.7.5, macOS Ventura 13.7.5, tvOS 18.4, and visionOS 2.4. Now, one thing you'll probably notice is those updates came out a while ago, probably maybe like a month-ish or so ago. So at this point, if you haven't updated to them, definitely, at this point, a lot of people say, do, this immediate thing after, you finish watching this. But no, literally pause this episode right now and update your device if you are not on one of those OS versions or newer. Literally pause the episode right now, update, and then come back. That's how important this is, because this is a zero-click exploit in some cases, which essentially means you literally just existing could get yourself hacked, which is basically the worst case scenario. Now, when it comes to the vulnerability itself, this wasn't something necessarily specific in like the kernel or whatever. It was part of the AirPlay SDK or software development kit. So patches for that SDK have been released as well. AirPlay Audio SDK 2.7.1, AirPlay Video SDK 3.6.0.126, and CarPlay Communication Plugin R18.1. So hopefully, if you have some other non-Apple device that supports AirPlay, definitely be on the lookout for an update if you haven't already received one, in order to hopefully implement that fix. Now, as we touched on, the whole idea of zero click. So, kind of like we said, what that essentially means is, unlike say a phishing email, where you actively have to like click on the link in order for you either to download the malware or go to the malicious site or whatever. Zero click, like I said, you literally just have to exist and you can get hacked. So in this case, with how AirPlay works, being interacting with like Bluetooth and Wi-Fi networks, literally as long as you're on like as kind of like the title suggested, which I will have linked in the show notes. As long like if you just log your device onto a public Wi-Fi network, you just doing that could get you hacked. And it doesn't matter if you have a VPN or anything like that. Just the fact of you being on the Wi-Fi network could get you hacked. Now, obviously, if you are updated your OS version to one of these newer versions, this vulnerability has been patched, so you don't have to worry about it. But the other tidbit to this vulnerability is the fact that it's wormable. And worms are one of those kinds of malware that they basically kind of self-replicate. So if you've never heard of what worms are before, essentially what they'll do is they'll infect a system and kind of implant themselves into the system, and they'll constantly kind of like scope out the network for other potential vulnerable systems. And then if they find one, they'll basically make a copy of themselves on that other system and basically kind of spread that way. So because this is zero click, literally what can happen is the threat actor can inject the worm onto a susceptible device, vulnerable device, and then that worm can basically just go to work searching around for other vulnerable devices and then copying itself onto them, and so on and so forth. So yeah, this is a very, very, very bad vulnerability. And to be honest, if it wasn't already patched, this would I'm pretty confident in saying that this would score a perfect 10 on like the vulnerability score, because I guess yeah, it probably would be a 10 because it's zero click. You basically get access to the system. Yeah, it's really bad. So like I said, I'll have a link down in the show notes if you want to read more about it. But on to our next cybersecurity news story, which also happens to be our cybersecurity tip for the week. This week's cybersecurity tip is a bit of programming 101, which is don't hard code any credentials, access tokens, API keys, etc. in your code.
No dip, Sherlock.
Well, thank you, Peanut Gallery. I'm glad you piped up there, because while you might think that that's pretty common knowledge, apparently it wasn't common knowledge to some developers at Cisco. Because this is a public service announcement that if you are using Cisco gear, specifically the 9000 series, you need to update ASAP. Because a newly discovered vulnerability with the CVE 2025-20188 in Cisco gear scores a perfect 10. So while we theorize that this potential vulnerability in AirPlay could be a perfect 10, this vulnerability is actually a perfect 10. Now, basically what happened here was it was discovered that there was a hard-coded JSON web token on affected Cisco systems that includes so basically the included list here is the following Cisco systems running a vulnerable release of the Cisco iOS XE software and have out-of-band AP image download features enabled. And this includes the Catalyst 9800 CL wireless controllers for cloud, Catalyst 9800 embedded wireless controller for Catalyst 9300, 9400, and 9500 series switches, Catalyst 9800 series wireless controllers, and embedded wireless controllers and Catalyst APs. So if you have any of those, or your company has any of those, you need to update as soon as possible. Now, according to Cisco, how this attack can actually be performed is, quote, an attacker could exploit this vulnerability by sending crafted HTTPS requests to an AP image download interface. A successful exploit could allow the attacker to upload files, perform path traversal, and execute arbitrary commands with root privileges. End quote. So yeah, that is a big oof. Remote code execution as root. That's perfect 10 material right there. So yeah, if you have one of these devices, like I said, you need to update ASAP. This is probably another one of those where literally pause the episode right now, go do those updates, then come back to this, because this is really, really bad. So yeah, if you thought it was programming 101 to not hard code your credentials inside your software or your firmware, you would be correct, but apparently it seems like not everyone took that programming 101 course. Because in this case, there were some hard-coded JSON web tokens inside these Cisco systems. So yeah, patch your Cisco systems if you were one of those that was affected. And that is your cybersecurity tip for the week. Now, moving right along, let's get into what nerdy stuff have I been up to this week. So this week, I got into something that I kind of wanted to do for a while. It's been kind of something in the back of my mind, and that is creating a weighted random number generator. And what I mean by that is, so you know how typically when you create a random number generator, or well, I guess you probably aren't creating one, but when you use a random number generator, you kind of give it a range, and then, so say you give it a range between, say, 1 and 10, you basically have an equal probability of getting any one of those numbers, right? But a weighted random number generator is you can basically give a subset of numbers and then give weights to each one of them. So say you give, there's a 50% chance that 1 could come up, and then like a 20% chance that 2 comes up, and then like a 10% chance that 3 comes up, etc. And then you would expect that 1 comes up 50% of the time, and so on. And the reason why this is kind of so important for me was, as you know, if you've been listening for a while, I am trying to create my own Pokemon game completely from scratch. And if you've ever played Pokemon before, you know that there are various encounter tables for all the various routes in the game. And basically what that means, and you've probably noticed, even if you didn't know that this existed in the games, is on some routes, some Pokemon show up a lot more frequently than others. And the way that's done is through some kind of weighted, random number generator, essentially. So there's many different ways that you could go about doing this, depending on how kind of fine-grained you wanted to be. One of the kind of initial kind of ideas that I had, which, to be honest, it wasn't really good, was to essentially create an array of, say, 100 elements, and then inside each one of those indices, basically set the Pokedex number of the Pokemon that I wanted to be in the encounter. And don't get me wrong, that would absolutely work, and you would have basically instant lookup time. It'd be a time complexity of O of 1 because you just create a random number between 0 and 99, and then you just index into the array and you get your random encounter, and that would absolutely work. But again, that's an array of 100 elements, so the memory space there is significantly larger than it needs to be. And here we kind of come into this. Maybe at this point you can kind of see where the inspiration for this week's episode came from. So it kind of came down to this. Okay, so that's obviously a good for performance solution, but not very good in terms of memory usage. Now, sure, if you only stored, say, like a 2-byte integer in that array, yeah, I mean that's still 200 bytes of memory, but in the large scale of things, it's not like super egregious or anything like that. But we can do significantly better. At least in terms of the memory footprint. So essentially, what I ended up settling on, at least for the time being, who knows, this may change by the time if/when this game ever comes out. But the current solution, if you will, is to basically create an array. Well, I guess at least in its current implementation, since I was kind of just prototyping, I haven't actually integrated it into the game yet. But at least in the prototype phase, it takes in 2 arrays of the same size, one being the possible encounters, or currently it's just just generic numbers. And then the second is the weights associated with those numbers. So for instance, the 0th element in the numbers array its corresponding weight would be the 0th element in the weights array, right? So and essentially how it works is the weights are a number from 0 to 1, and then the random number that gets generated is also from 0 to 1. So essentially how the algorithm, I guess, if you will, works is it goes through the weights and it adds them up until the random number is less than the weight sum. So for instance, if the random number that got generated was 0.75 and the first weight was, say, 0.5, it would go to the second weight. Say the second weight is 0.3, and that would be 0.7, so again still smaller. So then you go to the next weight, and then that one's larger, so now that's the index that we return, and then we get the number out. So that's essentially the general flow. Now, granted, this isn't as it's not as performant as the single array and you index directly into it, obviously, because at worst, this is an O of n operation, or essentially you have to go through the entire array before you can return your element. So technically speaking, it's not as optimized. But again, if you've ever played Pokemon before, encounter tables are, I don't know how big they are, like maybe 5, 6 is kind of usually the peak. Now, granted, with my game, I'll probably make some of them larger than that. But again, still, like, even if we're talking like maybe 10 encounters or so, I mean, even still, that's still, not very, very much in terms of complexity. Now, the other thing I kind of toiled with was to do some sort of like maybe kind of like binary search type thing and do, get it down to like log of n rather than O of n. But I don't know. I feel like you wouldn't necessarily gain too much with that. Plus, also, if you did that binary search thing, you'd have to do either 2 things. Either one, you'd have to pre-sort your encounter tables, or you'd have to basically ensure that they're always in sorted order. Otherwise, the whole fact of it being a binary search kind of falls apart. So I don't know. I just kind of like the complexity of it. Just the O of n solution. Sure, it's not technically the most optimized, but when you also factor in the optimization in terms of the memory footprint and the simplicity of it, I think it's kind of a nice balance of simplicity and memory and overall performance. So Who knows? I might change my mind by the time, like I said, I might change my mind by the time uh, it actually, I get to the point where I want to potentially release it. But the other thing that's nice about this too is because we're not dealing with a fixed size array, we can basically make the encounter rates whatever the heck we want them to be. So, for instance, like if you were dealing with, say, that array of 100 elements, you can only get as fine grained as a 1% encounter. Now, granted, that's basically as low as it goes in the games. But say, for instance, you wanted, to have a massive encounter table, and you wanted something to be really, really, really rare, and maybe you wanted it to only show up like, you know, rather than 1% of the time, like, 0.5% of the time or something like that. In order to get that kind of granularity, you'd have to massively increase that size of your array, which again would massively increase the amount of memory that you'd take up. Which is kind of the nice thing about this kind of weighted solution is the memory footprint, no matter how you set the weights, doesn't change. It's still whatever the number of your encounters are, and basically times, however big. I guess in this case we were talking about like 2 byte numbers. So basically, however many encounters you want times two, and then that's your encounter plus. Well, I guess plus the weights, but still significantly smaller than a ginormous array. And again, if you ever wanted to change the encounter rate, you wouldn't have to manually go into the array and change all the different values. Now, granted, I guess you could just loop through all that and kind of automate it. But again, when you're talking about looping through all that, that's again, more complexity. Now, I guess also you could make the argument that if you were doing something like that with encounter tables, well, yes, you would have to, like, say, loop through every index in that, say, 100 element array and populate that. Because that's a constant thing, since I'm using C++, you could just make that a constant expression and basically compute that at compile time. So when it actually comes down to the actual performance of the game, it would essentially be a non-factor. It would just be the array would already exist. It would already be pre-coded into the binary, which is one of the nice things about constant expressions, which we will get into in a little bit when we talk about these optimizations, is that's something that could be computed at compile time, which would be a benefit. But still, you'd have to write the code to manually do all that, which would also kind of be a pain. So like I said, I kind of like the balance and the trade-offs here, and that kind of is a pretty good segue into, talking about, optimizing for both memory performance, or I guess memory usage, and just kind of overall program performance and speed and whatnot. Because again, like we kind of touched on, there's always trade-offs that you have to kind of weigh. You have to weigh the pros and cons of, do I want this to have the smallest memory footprint possible, or do I want this to be as blazing fast as possible, and I don't care if I use, a lot of memory in the process. And depending on what your use case is, depending on what your application is geared towards, that's definitely going to weigh into your decision into which, side you tend to lean more towards. So I guess starting off first, we can talk about different memory optimizations. So when it comes to memory optimizations, it's basically just different techniques that you can use in order to better utilize memory and use it more efficiently, and also in some cases use less of it. So the first thing that you have to kind of think about when talking about memory optimization is how it's allocated and deallocated. Now, if you're not dealing with like a systems level programming language where you have to allocate the memory yourself, you really don't have much control over this. It's kind of handled by the language and behind the scenes for you. But if you are dealing with a language where you have to manage your own memory, like I am doing, you have to. This is where it kind of really comes into play and can be a very significant factor in how your memory performance and overall usage is. Now, when talking about allocation and deallocation of memory, one thing that you really have to consider is where your memory is being allocated to. Is it being allocated to the heap, or is it being allocated to the stack? Because if it's being allocated to the stack, that that's going to be a lot faster to access that memory compared to something that's on the heap. So in C, we have functions like malloc, calloc, mmap, realloc, free, and moomap, which are basically for allocating memory on the heap, and then of course freeing memory on the heap once you're done with it. Now, I guess we should also state the obvious here, that if you are allocating memory in your program, you should be freeing the memory in your program, because it doesn't matter if you have literally the most optimal way to utilize memory that's ever been conceptually thought of in existence if you never free any of the memory that you use. So yeah, memory leaks are bad. There are plenty of stories out there. I can remember a story back when I was in my doing undergrad, first learning C, where I think the professor was mentioning that like there was some program that they were working with that was written in C and it had a really slow memory leak. So basically the solution was to basically just restart the server after like, I don't remember what the cadence was. I don't know if it was like, I want to say it was like every 2 months or something like that. They would just have to restart it because it ended up taking up all the memory of the system. So yeah, memory leaks are not good. So that is something that you do have to remember. I think that kind of goes without saying. But when it comes to these allocators, they allocate memory on the heap. And when it comes to, how if you want like as fast access as possible, you'd want to deal with memory on the stack, and that's where like fixed size arrays come in. So whenever, like if you're in C or C++, for instance, and you create like a fixed size array, like you do say int value, square bracket 50 close square bracket, that's basically allocating essentially that memory on the stack, rather than if you did like a malloc call that which would allocate it on the heap. So the nice thing about the allocating on the stack is it makes the access of that memory a lot faster, because when the program is stepping through the different instructions, if it's already on the stack, it's basically going to, theoretically it should already be kind of in the cache of the CPU, whereas if it's on the heap, the CPU would have to basically go, it'd basically be a cache miss. The CPU would have to go out, pull that data in, do whatever it needs to do, and then potentially have cache misses. Now, if you're interested in hearing more about cache misses and cache hits, we'll get into that a little bit more when we're talking about performance. But we did do an episode, it was episode 101 of the podcast. We had a segment on there just diving super deep into like cache optimization. And I definitely encourage you to go listen to that as well. Yeah, so that's that. If you want fast access to your memory, the stack is where you want it allocated. But again, the kind of the issue with the stack though is if you're trying to allocate memory on the stack, it has to be a fixed size. You can't, reallocate that memory on the stack. It just really doesn't work. So like I said, when it comes to allocating memory, that's one thing you have to be mindful of where is this memory being allocated. But the other thing you also have to keep in mind is how and when you're allocating your memory. So, for instance, if you have a function that needs to call, say, malloc to allocate some memory to it, what you don't want to have happen is have that function be running sequentially or potentially very frequently in a loop. And the reason for that is whenever you call malloc, you're making a system call. And if you've kind of delved into, I guess this kind of goes back into the performance aspect of things, but rather than strictly memory. But whenever you're making system calls, basically what happens under the hood is your program stops executing. So basically when you make a call like malloc, you're basically telling the operating system, hey, I want some more memory. So then what'll happen is you'll basically cause an interrupt on the CPU, which will pause the execution of your program. The operating system will take over and basically do some operating system things and then return you the memory that you asked for, assuming that it succeeded. And then your program can continue on. And if that sounded like a decent amount of steps and might take a little bit, you're right. Now, of course, if you just, run a program with a malloc call, it's going to be basically, instant. You're not going to notice anything. But what you will notice is if you write a function that, say, loops, I don't know, like 100 times, 1,000 times, whatever, and you're calling malloc in there every single time versus creating like a statically allocated array, what you're going to notice is the version with the statically allocated array is going to run circles around the malloc version because of that system call and that latency. So if you are using a function that gets called repeatedly, like in a loop, as best as you can, avoid making system calls like malloc for accessing memory. And this is kind of a nice segue into the next type of memory optimization type thing you can use, which is memory pooling and caching. And basically, the idea of memory pooling is to have a centralized location of data that you can have access to. And it's the same thing with caching too, like in kind of like a similar vein. But memory pooling is a fantastic solution for those instances where you're doing a loop, you're constantly looping, and you need memory allocated in that loop. If you have a memory pool, you can just access that memory pool, so you're not allocating memory every single time you're going through the loop. Now, of course, you have to make sure that the memory that you would use, there's enough memory in the memory pool in order to do that. But it is a much more efficient way of utilizing that memory compared to making malloc and free calls every time you're looping through. Now, the other benefit of doing a memory pooling solution is typically, if you're doing a memory pool, you can do it with like a malloc call or like an mmap call, but I think a lot of times, at least that I've seen, when people want to do like a memory pool solution, is they basically statically allocate the size of the pool. And the benefit to this is because they're statically allocating it, that memory's on the stack. And again, like we said, the stack is a lot faster than the heap. Now, one thing again you do have to keep in mind is the stack isn't as big as the heap is, so you do kind of have to be a little bit cautious there when it comes to memory pooling. But because it's on the stack, you statically allocate it, that can be basically ready to go when the program runs. You don't have to essentially run the program, allocate the memory, and then you can start executing. The memory's already there and you can start going right away. So definitely a more efficient use of of the memory. Now, caching is similar in the sense that you're essentially keeping recently accessed data close rather than having to retrieve it all the time. Now, again, kind of like we talked about in the, I think we touched on it a bit. Maybe we didn't. I don't remember. It was a while ago. The cache optimization thing with the CPU. When it comes to how the CPU accesses memory, first it looks in its cache. There's at least in modern CPUs, there's typically three layers. You have your L1, L2, and L3 cache. L1, of course, being the fastest, and then L2, and then L3 is generally shared between like all of the individual CPUs on the package. And then of course you have system memory, which is even slower than cache, and then of course you have your disk space, which is even slower still. And every single one of those cases where the CPU looks for something and has to go to the next tier of memory, if you will, accrues additional overhead. Now, sure, a one-time thing, you're probably not really going to notice it. But again, like we demonstrated in that episode where we talked about cache optimization, when you're hitting that, say cache misses is what it's called, over and over and over and over and over again, you notice it really quickly. It's kind of like a compounding thing that builds on itself. So again, because storage is significantly slower than even RAM, there's going to be a lot more overhead trying to, say, read in data from a file than if you already had that file read in and sitting in memory somewhere that you could just pull from. So that's kind of what the concept and idea of caching is for. Now, caching, as far as like memory utilization goes is almost certainly going to increase your overall memory utilization. But it can be a very good strategy, especially if you're, dealing with slower storage, like say spinning Rust. It can be a good solution to kind of, a way to essentially utilize memory in a very efficient manner, keeping things in cache. And this is something that ZFS does pretty well, and why ZFS can be still fairly performant even when dealing with a bunch of spinning hard drives, is because it basically has a cache pool which basically uses your memory, like all the memory that it basically can get its hands on, to basically store recently accessed files and basically keep it as a cache, to basically allow for faster read and write access, which is definitely a benefit, which is something that cache can do. The tricky part when it comes to cache, though, is how you implement the cache, because inevitably you're going to run out of memory. So, how do you decide what memory to evict and say right back to disk versus what memory do you keep inside the cache? Now, there's a lot of different ways that you can go about implementing it, which we'll kind of touch on when we get talk about the performance aspect. But that is something to kind of keep in mind. The next kind of thing I wanted to talk about when talking about optimizing memory usage is data compression and encoding. Now, this is kind of more of a specialty case, and this is one of those big things where there's an obvious trade off when it comes to performance. Because while, yes, compressing and encoding data will be one fantastic way to reduce the memory footprint that you use, because obviously, if you can compress, say, like, 10 kilobytes of data down to, say, 1 kilobyte of data, sure, your memory usage is going to be significantly reduced, but then anytime you want to access that data, you have to, decompress it, which has performance overhead associated with it. So it is something you do have to be mindful of. Now, I will say, if you do look at, an operating system like macOS, for instance, macOS makes use of compressing memory pretty heavily, I've noticed, especially on systems that don't have as much RAM, which, if you've used an Apple device in the past few years, you're probably well aware. Only recently did they upgrade all of their devices, all their at least laptops and desktops and everything, to 16 gigs. So if you're out there, rocking like 8 gigs of RAM on Mac OS, you're definitely going to be seeing this, and even 16 as well to a lesser extent. But if you go to the activity monitor, what you'll notice, if you go to the memory tab, is there's like a specific thing associated for compressed memory. Now, currently, right now, I actually have it pulled up on my Mac Mini here. It says I have essentially 3.5 gigs of compressed memory. So essentially, what Mac OS is doing there is memory that basically data that it wants to keep in RAM, but maybe you're not accessing as frequently. It'll essentially compress that down to reduce the overall footprint, to keep more stuff in RAM. So the benefit there, if you compress memory, is you can keep more stuff in memory. But like I said, the downside is whenever you want to access that, you then have to decompress it, which does have performance overhead. Now, depending on how you're compressing data, depending on if you're doing it like on a file by file basis, or if you're doing it like on a block basis, you might not necessarily have as much performance overhead as you might think. Like we mentioned, 3.5 gigs is a decent amount of memory to be compressed. But if that's like a file by file basis, decompressing a single file probably isn't going to be as big of a performance overhead as you might think. Now, is it going to be one? Absolutely. But it is, something that you do have to be mindful of if that is a route that you want to go down. Now, when it comes to kind of utilizing some of these memory optimizations, one of the most notable ones that you basically have to pull out all the stops when it comes to memory optimization is embedded systems, because embedded systems are notorious for having very little amounts of RAM, and generally their processing power isn't all that great either. So some of the common memory usage and optimizations that I've seen when it comes to embedded systems is memory pooling is a big one. So essentially, at the very beginning of the program's runtime, allocating a large amount of memory for the program to run with, and it can basically access that memory pool, so you don't have to worry about the overhead of system calls, and you basically have that single source of memory that your program can use. So definitely a big boost there. And then mobile devices is kind of another use case. Now, mobile devices have definitely become a lot more performant in the past few years. And data compression, I think, is kind of probably the kind of more the route that they want to go with that, because obviously, if you're on a, say, like your phone, the last thing you want is for apps to take forever to open. Now, you can only keep so many apps in memory, but if you compress some of that memory, you can keep more apps in memory. So while maybe it might take a little bit longer to, say, decompress and open up the app, it's going to be a lot quicker than if the app wasn't, in memory at all. And then, of course, cloud computing is kind of another big one. Cloud computing caching is basically the name of the game in cloud computing, because you want everything to be as fast as possible. So the more things you can kind of keep in memory, keep in cache, the better. So, kind of moving into the next segment, kind of focusing. So, we touched on a lot about memory and memory optimization and performance. So, now I want to kind of shift gears a little bit and talking about the performance aspect of things. So, we touched on it quite a bit in the memory section. So, let's just address it right now: cache optimization. Now, there's kind of two parts to this. There's the one hand where you're talking about the CPU cache optimization, which again, we kind of did an entire segment about this, so I won't go super in depth. But if you do want to listen more about it and learn more about it, which I highly encourage, that was episode 101, titled Tech Buzzwords Decoded, 40x Performance with Cache, Writing MS-DOS Code, Operation Core Dump. So go listen to that if you're interested. But the short version is, if the memory you're trying to access is all very close together, basically the proximity of the memory you're trying to access, if that proximity is very close, the likelihood of you'll have a cache miss is significantly reduced, which means your CPU can perform more operations without essentially having to take the additional cycles to basically go reach out to the subsequent layers of memory, cache, whatever, to bring in that memory and then continue execution. But then there's also the other side of cache, which is kind of the cloud computing, I guess, definition of cache, if you will, which is having, large chunks of data in like a cache memory pool, or like whether that's files or whatever the case is. So essentially kind of how this works is, whether that data is from like a file on disk somewhere, from a database, you essentially kind of hold that in cache. But this kind of comes back to the question of, how do you decide what stays in cache versus what gets written back to the database or written back to the file system. Now, like I said, there's a few different strategies, but I think one of the most common ones is basically keep everything in cache until you have no more memory. And again, this basically means massive memory footprint, but massively increased performance as a side effect, because if everything's in memory, it's going to be a lot quicker to access something from RAM than it is to go out to the disk, read the file into memory, and then, send it on its merry way or do whatever you need to do with it. If it's already in RAM, it's a lot quicker to access. So one of the most common strategies, like I mentioned, is you basically keep everything in cache until you have no more memory. Now, when I say you have no more memory, I don't necessarily mean that your system has completely filled up its RAM. Because what you could also do with a cache pool is you could set a limit to it, right? So you could say, like, if my system has, say, since we're talking about servers, say my system has a terabyte of RAM, but I only want, say, 500 gigs of that to be allocated to cache. Then once the cache reaches that 500 gig mark, then you kind of have to get into the debate of, how do I manage this cache? So that's what I mean when I say you run until you basically fill up memory until you run out. So there's a couple ways that you can kind of do this. Like I said, probably one of the most common ones is you basically evict the oldest data, right? So one way that you could do this is you have some kind of table or some kind of hash map or however you want to store it, but you basically keep a timestamp of when that data that's currently in cache was last accessed, and whichever one's the oldest one, you basically get it out. Well, I guess technically you could evict multiple things from cache if you needed to, you say, pull in, a larger, say, file or whatever that wouldn't fit, and maybe you have to evict like 3 files in order to bring that one in. But then that also kind of begs the question of, another idea when it comes to optimization is, do you bring that large file in? Or do you keep the cache specifically for small files? Do you keep the cache for large files? There's a lot of things that you kind of have to think about when it comes to how you're going to be managing your cache. But like I said, one of the most common things is you basically just evict whatever the oldest thing is. But that doesn't, like I said, that doesn't necessarily mean the oldest item that was put in cache, because say, for instance, there was a file, say index.html, say you're running like a web server. If index.html was the first item to be put into the cache, but it's being accessed, say, like every few seconds or whatever, of course that's going to have an updated timestamp, and it's not going to be technically the oldest thing in cache as far as the timestamp goes, because its timestamp is going to keep getting updated. So that's kind of one way that you can kind of manage it, because of course the files that get accessed frequently and repeatedly are obviously the ones you want to be in cache, right? Which is kind of why that strategy of basically evicting the oldest thing to bring in something else is kind of the I guess the default, if you will, strategy when it comes to cache management. But again, like we mentioned, kind of the downside to that is if you say have a bunch of small files in cache, but then someone wants to access this massive file that's going to evict like half of your cache just for that one file to be put in there. Is that something you want to do, or do you just kind of like read it and send it on and not put it in cache? So, like I said, there's a lot of different strategies and kind of methodologies and theories you kind of have to think about when designing your cache structure. But, just kind of as a, I guess, baseline, that's kind of what we're talking about. The next thing in terms of performance is compiler optimizations. Now, if you aren't using compiler optimizations, you absolutely should be, because they have definitely come a long way. Now, I've talked before, I'm pretty sure I mentioned this before one time on the podcast, about how enabling optimizations. There's this one instance where I was trying to basically do a comparison between multi-threaded performance. I think I was using C++, I think, or maybe it was C. I don't remember. But the point is, I was trying to see what the performance difference would be. Basically doing a very basic sum, right? So I take like, what is the sum of every number from, I don't know, like 0 to like 10 million or something, or some like really large number. But what happened was, when I turned on compiler optimizations, the compiler noticed that I was essentially doing this sum operation, and as part of the compile process, pre-computed that and stored it inside the binary. So rather than it actually going through the for loop and adding it up, it just printed the result because it already pre-computed everything, which basically defeated the entire purpose of the test. So what I had to do was, I think what I ended up doing was basically passing in the number as like uh, basically I used a variable and passed it in as like an argument, like in the command line, to basically bypass the compiler pre-computing the sum. So yeah, compilers have definitely come a long way. Now, I touched on earlier in this podcast episode about constant expressions in C++. Now, I want to say that is a C++ 2017 feature. So if you're using an older version, you might not have access to it. But if you're using any modern version of C++, you'll have access to constant expressions. And essentially what constant expressions are is it's basically a way for you to tell the compiler, hey, this is something that you can probably compute ahead of time at compile time, rather than me having to do this operation every time throughout the program. And that is a huge thing when it comes to the overall performance of your program, because the more work and computation you can do at compile time, the faster your program's going to execute at runtime. Because if you can remove a lot of those constant computations that you would otherwise be doing while the program's running and shift those to computing it once at compile time and storing that value inside your binary, whenever you get to that point where you'd otherwise have to compute it, if you can just input the number or input the result and go on your merry way, you're going to save a significant amount of CPU resources. Now, if you want to dive even deeper into constant expressions, Dave's Garage on YouTube did a very good video kind of demonstrating how constant expressions can be used and to significantly increase the performance of your programs. So I definitely encourage you to check that out. And actually, I'll try, if I remember, I'll definitely try to leave a link for that in the description and down in the show notes as well. But like I said, in short, now I guess I also should mention that just because you say something is a constant expression doesn't mean it'll be computed at compile time. It's basically just kind of a hint to the compiler that yes, this could be something that you can compute at compile time. But if you're using like variables that could change, probably not a good use of constant expression. But if you're using, say, like some like complex computation that needs to be done, but it's all the values are known like at compile time, then that is absolutely something that you would essentially be using constant expression for. So that could be something that even not necessarily turning on compiler optimizations, you might be able to take advantage of. But again, compiler optimizations can find some very interesting ways to optimize your programs to make them run faster. So if you aren't using compiler optimizations, definitely make sure you use them. Now, I guess one thing I should mention too is going back to that episode we did on cache optimization. If you aren't optimizing for cache performance and you're basically using the CPU cache in the worst way possible, as we found in that episode, it doesn't matter what compiler optimizations you use, you're not going to notice any kind of performance increase, because if you have that many cache misses, there's really not much the compiler can do about that. Now, I guess the compiler theoretically could rewrite your code to make it more cache optimized, but again, the problem with that is the compiler is essentially rewriting your code, and depending on what you were trying to do, maybe having all those cache misses was actually important for whatever computation you were doing. Now, is it not? I don't know. But the compiler just kind of making that judgment call is probably not something you want. But I guess that's neither here nor there. But when it comes to, types of applications where the performance of the application is critical, and kind of, I guess, memory usage, like who cares? Like, use all the memory we can. Any kind of like scientific simulation type stuff, anything gaming or graphics related, and anything like high fidelity trading type things, because like let's take gaming for instance. Of course, you're going to want the highest frame rates possible and the best performance out of the game to get the best experience. And if you've seen kind of the explosion in memory usage of video games, I think it's kind of evident which route they took. They obviously went the route of optimized performance. Now, to their credit, if you've looked at a game that was, say, created in the past like couple years, the graphics quality is going to be significantly better than something that was created in, say, the 90s. Now, in fairness, a game that came out in the 90s and in the moment absolutely looked incredible. And I can't tell you like how many times I've gone back to like older video games and been like, wow, this is what the graphics look like. I thought from what I could have sworn they look better than this. Now, in fairness, there have also been times where I've gone back to old video games and was like, wow, these graphics are honestly really holding up pretty good. prime example of that, I think, is like Gen 3 Pokemon games. Like, I don't know, there's something about like the sprite designs in those games that like even essentially 20 years later, oh, in some cases over 20 years later for like the first games in the generation, like I don't know, the graphics just look really good, especially if you can like play it on say Nintendo, close your ears, an emulator, and scale up the resolution to something a lot larger than the very tiny like Game Boy Advance screen. It looks really good. And if you know anything about some of the crazy wacky uh optimizations that went into like old video games, it is something else. But yeah, like I said, typically, at least in modern day, it's like let's optimize as much as we can for performance, and if we use extra memory, so be it, because we're already mandating that the user have X amount of RAM anyway, and it'll be fine. So now I guess let's talk briefly before we wrap up about some of the trade-offs when it comes to optimization. Now, personally, I am a fan of how things were in the old days. Now, yeah, the whole back in my day, so call me a boomer, whatever, I don't care. But back in the day, developers actually had to make this trade off. And it was a very conscious decision of what are we going to do? Because the systems that they were developing for were a lot more resource constrained than they are today. Like today, you can basically run whatever you want on whatever you want, and it'll generally perform pretty good. Like if you run any piece of modern software on any type of computer that was made within the past, like, I mean, at this point, like 10 years, it's probably going to run fairly decently, if not fantastically. Which cannot be said, back in like the early 2000s and the 90s, right? If you were, say, running a game, say you're trying to run a video game, for instance, say in the year 2002, and you were trying to run it on hardware from 1992, it's probably not going to work at all. So there has been significant leaps in computer performance, both in terms of CPU performance and in terms of memory utilization. Since the CPUs of yesteryear, they weren't exactly the multi-core monsters that we have today. And similarly, back in the day, systems had, megabytes of RAM, or if you want to go even further back, kilobytes of RAM, not gigabytes, or in the case of the high-end server world, terabytes of RAM. So I guess what I'm saying here is you could, go with the leet code hack of throw everything in a hash map and call it a day, but that's not going to get you the optimal memory performance. Now, one thing that I think I've kind of documented fairly well, if you've listened to the podcast for a long enough, going through my journey of developing my video game on my very hot and cold when I actually work on it streak, one thing that I have been very dedicated to is trying to make it use as basically make use as little memory as possible. Like the goal of this project, well, I guess there's multiple goals, but one of them is to kind of make a video game like they were back in the day, right? Like make it so like optimize for memory usage and not be like, who cares if this isn't, the most optimized date, struct. Yeah, the memory's not fully aligned and I used an extra eight bytes worth. Who cares? Yeah, that 8 bytes gets multiplied by however many Pokemon there exist. Say there's 400, so 8 times 400. Who cares? That's not the methodology that I'm taking in this at all. Like I'm trying to make it as memory optimized as possible while also trying to optimize for performance as well, and not do things that are like O of n squared, for instance, as far as like as far as time complexity where I can help it. So trying to, find that balance of both memory usage performance, or I guess just memory usage in general, as well as overall performance is something I've been really trying to find a balance in. Now, granted, have I always gone with the most optimal memory usage strategy? Probably not. Have I always gone with the most optimal, algorithm usage? Again, probably not. Some cases I've even found that like the way I was doing things was horrible, and I figured out a much better way to do them, and that's happened on numerous occasions. So yeah, but again, when it comes to like trade-offs and optimization, it really again comes down to what your use case is. Like a couple examples, I guess from the video game that I'll touch on kind of briefly here, is when it comes to instant lookups for the Pokedex. So what essentially how I went about solving the idea of how do I do Pokemon lookups. Probably the I guess the leet code solution would be throw it in a hash table, and then you can just do an instant lookup and bada bing bada boom. I could do that, or I could just create a fixed size array because I know there's going to be a set number of elements in the array anyway, or inside the hash map. And if I just order the Pokemon in there in terms of their essentially their dex number, I can get an instant lookup with the array, have significantly less overhead and reduced memory space, and not have to deal with all the complexities and overhead that comes with dealing with a hash map. So, in my opinion, that's kind of a win. The other kind of big one I had was, the when it came to getting names for things, like the names for items, abilities, natures, whatever. I think there were some other ones, but I don't have to. Types, I think, was another one. I could have obviously put that into a hash map. It has a string key for what the name is, and then it spits out the result, right? And that would work as a hash map. Or I could create an enum and basically get the same, functionality as entering a string into a hash map. You just type the name of the variable, which is very human readable, and then index that directly into an array, have single, O of 1 lookup time, O of 1 complexity, takes up less space. It's just a single array, don't have the additional overhead of the hash map, and bada bing, bada boom. So yeah, so now I think this kind of goes without saying that I'm putting hash maps in a very bad light, which don't get that impression because I am also using hash maps inside the game as well for other uses. But what I'm saying is not everything has to be the leet code solution of everything goes in a hash map. That's in some cases, that's not, at least in terms of memory usage, not the most optimal way to do things. Now, again, one thing with like hash maps, as we kind of touched on, there's additional performance overhead when it comes to computing the hash. Now, yes, as far as time complexity goes, it is an O of 1 operation, meaning you basically compute the hash and you index directly in and get the element, and it's essentially an instant lookup, just like an array. Now, I guess there is some slight caveats to that with a hash map, depending on how it's laid out, but for and what hash function you're using. But for the sake of argument, you're using the best hash function ever, and it's an instant O of 1 lookup. But technically speaking, if you index directly into an array, it will be faster. And the reason for that is because, like I said in the hash map, in order to get the value in the hash map, you first have to perform a hashing operation on the key in order to get the index of where the value is inside the hash map in order to return it. You don't have to do any of that if you're using a fixed size array with an index. You literally index into it directly and you get the value out. It's significantly faster. Now, again, are you going to notice that in a kind of a one-time use operation? Probably not. But if you're doing it repeatedly over and over and over and over and over again, probably that's kind of the case where you might actually start to notice it. So again, in the case of the overall scope of this game, would you actually notice a significant difference using a hash map versus my array kind of lookup thing? Almost certainly not, especially on modern hardware. But that's not the point of this. The point of this, at least for me, and kind of the strategy and reason. So I, of course, made the judgment call, right? Of I wanted to optimize for the maximum amount of memory, minimize the memory utilization while also trying to maximize performance. Not necessarily going with kind of the easy solution of just throw it in a hash map. And that was a conscious decision on my end and a design choice on my end, which, in all honesty, if I was actually at my job creating and writing and developing software, that's probably not the solution I would end up going with. I probably would have gone with the hash map solution if we're being honest, because again, there's different priorities there, right? Like for me, like I've mentioned before, my priority was minimize memory utilization, maximize performance, and in kind of the I guess the corporate world or whatever, or depending on where you're working or what kind of software you're developing, that's probably not necessarily a thing that they would care about, and they would be like, hash map makes more sense. It's in terms of like implementation, you don't have to worry about essentially managing like an enum structure as well as an array, and technically you could make the argument that it's less complex in that sense. But again, these are all trade-offs that you kind of have to kind of think about when you're making these kinds of memory and just overall optimization decisions. So I think I've kind of rambled on on that enough. I noticed I was kind of starting to repeat myself, so I think we'll probably just stop it there. But before we go, I think we should probably get back to our trivia question for the week, which again was a true or false question, which is true or false. Using malloc guarantees the memory you receive will be initialized with all zeros. If you said true, you are thinking of calloc, not malloc. So the answer is actually false. So if you said false, congratulations, you got this week's trivia question correct. Now, I guess it does go without it is worth mentioning, depending on the environment you're using, there is a chance that malloc would actually return all zeros, but per the C standard, it's not a guarantee. So yeah, just kind of a fun fact there. So that's going to wrap it up for this episode. But if you have any topics, ideas for future episodes, or I know we talked a lot about some kind of complex things in this episode. So if you have any questions or anything that you want clarified, definitely either leave a comment down below if you're on YouTube, or you can shoot me an email at contact@darkassassinsinc.com. And if you enjoyed the episode, definitely leave it a rating and review and subscribe if you haven't done so already. If you're on YouTube, leave it a like. And if you haven't done so, also share it around with friends, family members, all that good stuff. And yeah, that's going to do it for me in this episode of the Dark Assassins podcast. Until next time, my fellow assassins, remember, bool nothing equals true. If action not equal to null, return true. I'll see you next time on the Dark Assassins podcast.